Hello, welcome to Data Science with EJD. In this video, we are talking about regularization techniques, which also fall under regression. And here, our focus is on ridge and lasso regression. There are actually three types of regularization regression techniques. We have ridge, lasso, and or a combination of both, which is called elastic regularization. So, learning objective is to understand the need for regularization in a regression to avoid overfitting. So, I mean, one problem that can arise in machine learning is overfitting, and one way to deal with that is to, regularize by using regularization techniques like ridge and lasso. So, learn the difference between ridge. Ridge is called L2 regularization, while lasso is called L1 regularization. Interestingly, lasso has a full name. I think let me see. I don't remember what that is, but we can quickly check that up. Lasso. Okay, lasso is a loop used for catching those. No, 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 that's not the idea I'm looking for. Lasso in full. Lasso in full. I think that's better. Lasso in full. Yeah, it's least absolute shrinkage and selection operator. Least absolute shrinkage and selection operator. It is a statistical formula for the regularization of data models and feature selection. So you soon see how how each of them performs like that. So you want to also apply ridge and lateral regression on a real data set using Python, then compare the effects on model coefficients and prediction performance. So let's talk about the introduction. Why do you have to regularize? Of course, obviously because of overfitting. So in linear regression, the goal is to model the relationship y equals beta x, not usually the beta would come first, beta x plus epsilon, which is some error in what you're doing. So, however, when the model is too complex, e.g., many features, or if you have too many features, or you have features, or you have many features, well, I mean, a model can be complex when you have many features or there is a lot of multicollinearity. Many of the variables or features but they behave the same way. Okay, so what can be done sometimes is you want to drop some models, some features that look alike because they are multi-collinear. They are both collinear. So the model can overfit training data, resulting in poor generalization when you have complexity. So overfitting leads to large variance and unstable coefficients. So that's why we need regularization. Regularization now introduces a penalty to reduce complexity and improve model generalization. So let's talk about ridge regression. That's what we call L2 regression. So regression adds an L2 penalty. So I think L2 penalty is some mathematics thing. So this L2 penalty is the sum of squared coefficients, and that's exactly what you have around here. In fact, okay, this is the penalty time lambda, right? So this is a regularization parameter, and then this is the square of the sum of squared coefficient to the loss function. So here lambda, which is greater than or equal to 0, is the regularization parameter controlling the strength of the penalty. Okay, so then when lambda is 0, you see that the whole thing just becomes like ordinary least squares, which we've done in statistics or even optimization techniques before now. So this term is what is adding the ridge regression to it, which brings in an L2 penalty sum of squared coefficient to the loss function. So then you have when lambda approaches infinity, you see coefficient. So as lambda goes towards infinity, coefficients shrink towards 0 but never become exactly 0. So in ridge regression, the coefficients never ever become exactly 0, right? But they get to shrink towards 0, but not exactly at 0. Okay, so then the key points controls uh, ridge regression controls magnitude but does not eliminate features, right? So it would still give you something like linear regression where you still have all the coefficients and everything, but it would have done its work a little bit. Then it is effective in dealing with multicollinearity. That's where you have many correlated features, and then it produces stable and small coefficients. Stable and small coefficients. But then on the other hand, lasso regression does something even more drastic. Lasso regression it can also be seen as L1 regularization. So Lasso regression adds an L1 parameter, which is the sum of absolute values of coefficients. So you see, this is it now. Sum of absolute values of coefficient. So that's the main difference. You have sum of absolute values of coefficients, whereas up here you have sum of squared coefficients. So sum of squared coefficients, Ridge, sum of absolute value of coefficients, Lasso. Now, similar to Ridge, lambda controls regularization strength. So the lambda is still in both cases. So you have lambda here, which still controls the strength of regularization. But unlike Ridge now, Lasso can shrink some coefficients exactly to zero, performing feature selection. So you can have some values going exactly to zero for Lasso, right? So the key point here is that it encourages sparse models by eliminating less important features. So, but by its very essence, Lasso helps you to push some features to zero because they are not that important. And it is useful when you expect only a subset of features to be important. The model interpretability improves due to automatic feature selection. So because some features are automatically eliminated, then you can know the features that are really very important using lasso regression, right? So that's what that has been. Um, so let's compare Ridge and Lasso regressions, L2 and L1. So talking about the penalty, we have for Ridge, we have the sum of squared coefficients. For Lasso, we have sum of absolute coefficients. For shrinkage now, for Ridge, shrinks coefficient towards zero, but it doesn't ever get to zero. But Lasso shrinks and forces some coefficients to zero to show that they are not actually important. Of course, from Ridge, you can still know they are not important by looking at their magnitude. But Lasso just shrinks it to zero to just show you these features are not important. Now, for feature selection, so in Ridge, no, all features are retained. But in Lasso, some coefficients go to exactly zero to show that these features are not important. Then we talk about effects of multicollinearity. Ridge stabilizes coefficients while Lasso selects one feature among correlated group. So if you have many correlated groups, so Lasso just picks one that is most important and shrinks the rest to zero. So automatically helping you to take care of that problem. Then you have model complexity control. Ridge controls size of coefficients, while Lasso controls size and sparsity. So it takes care of the features themselves, like drive some features to zero and just retains what is really important. Then the use case, in Ridge, when many features contribute, you can use Ridge. Then in Lasso, when few features are important. So if you need few features, if you just need few features, you need to use Lasso. But if you cannot do without one of any of the features, then Ridge is your go-to method. Okay. Okay, I think I have to reopen this. It's gone now. Ridge and Lasso. Okay, yeah, back here. Okay, let me just keep running. Okay, so let's come to something practical now. Practical example, Ridge and Lasso on California housing data set. The same data set we used for linear regression, we used for polynomial regression. Now we are using the same for Ridge and Lasso. So we will load California housing data, standardized features. That's so for to do regularization, we need to standardize features, and we also need to we'll fit Ridge and Lasso regression. We evaluate and compare model performance and coefficients. So these are the step-by-step code implementation. First of all, we import required libraries. Of course, for machine learning, scikit-learn is the most important library. For data analysis, right? We already know pandas is the most important library. So if you stretch it a bit further, after scikit-learn, you are going into things like PyTorch, TensorFlow. In fact, TensorFlow and then PyTorch also, right? So import libraries, scikit-learn for the most part, where you get the data set from the linear model. We are using Ridge and Lasso. Their model selection, of course, the usual thing, train test split, like about the most consistent. Then the preprocessing, if you need to do some scaling, then you need some metrics too. Here we have mean squared error, and then you want to you need some plotting. So we also need some data analysis to do before, and then NumPy. We have all of this. So don't forget to run. So we run this. It's working. Yeah, done. Then we load the data set. So for the California data set, now we have California equals fetch California housing. So XY. So X is the California data. That those are the features, while the target is California.target, right? So the feature names are so it means the data set have been preprocessed for use in machine learning. That's why we can have this. I think it's important to see the line to show the line numbers, right? So here we run this and that is done. Then we can visualize the X. So we see the X. So these are the features for this. And here, of course, it's housing price we are still concerned with, right? So we've seen this data set before. So now we can now split into training and test sets. So as usual, X train, X test, Y train, Y test. So train test split X, Y. Test size is 30%, random state is 42. So don't forget to run that. Then standardized features. So you need zero mean and unit variance. So that's some I think we did this under feature engineering. I think under data analysis with Python using pandas. So you need some scaling. You want your data to be normally distributed. So you bring the scalar. So you say scalar is standard scalar. So for the X train, you have to scale the X train. That's scalar.fit transform X train. X test scaled. So you have scalar.transform X test. So run this and that is done. So the next thing you want to train ridge regression. So you have ridge is equal to ridge alpha 1.0. Alpha is lambda. That's regularization strength. So remember that lambda that we have, you know, that lambda we have in that equation, this lambda here. So, but we are dealing with ridge now. That's this ridge here. So that's the alpha in this case, right? But we use alpha for it, but it's actually the lambda. So alpha is lambda, the strength of the regularization. So if you want to make it harder, you can increase the value. Then you can now have ridge.fit x train scaled y train. Then you can now predict the ridge value, ridge.predict x test scaled. So you run that and you get something. You do the same for Lasso. But for Lasso now we have the alpha, the regularization strength is 0.1. So we say Lasso is Lasso alpha 0.1. Lasso.fit x train scaled y train. Then y pred for Lasso, that's the predicted value. So we have trained both ridge and Lasso regressions. Then we need to evaluate the performance now. So you need root mean squared value for ridge, root mean squared value for Lasso, like this, and then you print the values out. So for ridge, we have 0.728. For Lasso, we have 0.815. Now, okay. So, I mean, to be very sure, since RMSE can be quite a problem to interpret, so let me just say interpret. So I'm just asking Google to interpret this. Or okay, if that isn't working, let's go for Grok for interpretation. Okay. So we just say interpret. Okay, so we get ridge, RMSE for ridge. So the provided metrics ridge 0.728 and Lasso. This represent the root mean squared error for two different regression models, ridge and Lasso, likely evaluated on the same data set. Here's an interpretation. So generally, root mean squared error, this is a measure of the average magnitude of the prediction errors in a regression model expressed in the same unit as the target variable. So lower RMSE values indicate better performance. Yes. So for RMSE, lower is better. For R squared, higher is better, right? Closer to 1 is better. So the ridge regression model has an RMSE of 0.278. This suggests that on average, the predictions from the ridge model deviate from the actual values by approximately 0.728 units. Since this is lower than the Lasso RMSE, the ridge model is performing better on this dataset in terms of predictive accuracy. So Lasso RMSE is 0.815. So for RMSE, I think, yeah, so that's clarified. Now for RMSE, the lower is better. So it means ridge is doing better. But I mean, one thing I've noticed here is for Lasso here, we used an alpha of 0.1. What if we do 1.0? So I do 1.0 now, then I go back here, and then now you see, oh, it's even worse. It's even worse because smaller is better. Okay, so 0.1 seems even better than 1.0. Okay, what if we do 0.01? Okay, and then we now come here and do this. Okay, so this is 0.01 is fairer. So the strength. Okay, so let's do something that is this close. Okay, so now let's do the coefficient based on all those things we've done. Now you see, um, So Lasso drives this one. So it means population doesn't matter in this situation. Population of the environment doesn't matter. And then so, I mean, population has the least significance, even in ridge, but it doesn't ever go to zero. That's the thing. So, what if we make the lasso, if we make it harder, like what we had initially, and then we come back here, and then we have this now. So you have more. So you see here that more values are going to zero. So it all depends on how you want it to be. So here now it automatically tells you that the most important features are median income and the age of the house, then latitude. That's all. So beyond that, nothing more. So if you want some values to go to zero, so the stronger the alpha, the lambda, the more sparse the coefficients will be. So it's all over. It's all depends on what exactly you want. Then you can visualize these coefficients if you like. So you just do some plots for both ridge and lasso to visualize this coefficient. So see how this goes now. So you see, ridge comes all the way down, but lasso is constrained to uh, zero. Like anything that's going negative or uh, well, maybe negative is allowed sometimes, but here everything is just restricted to zero like this. So here you have the root mean squared error shows prediction error on test data, and like we've learned, root mean squared error, this the lower the better, right? So, but for R squared, the higher the better. So compare which model predicts better on unseen data. Of course, we see that here ridge does better based on the RMSE. The ridge coefficients are generally smaller but non-zero. Lasso coefficients have some exactly zero, indicating dropped features. So here now, all these values that went to zero, it means that those features can be dropped. So you can basically work with all the other features that are still retained. All right. So this visualization helps identify important variables for the model. So the ones on the positive side are more like what you really need. For Lasso now, median income and housing age are more like the most important things, right? But of course, for Ridge, you still have every other thing. Like we learned previously, right? You use Ridge if you can't afford to lose any feature, but you use Lasso if you don't care about any feature that is irrelevant, right? So the scenario, all features contribute. So when all features contribute and you prefer stable weights, you use ridge regression. If you expect sparse model with feature selection, you just want to select few features that really make sense, that really contribute to use lasso. If you want a balance between ridge and lasso, you can use elastic net, which is which combines both L1 and L2 regularization. So these are the three types of regularization. Okay, so the extensions, just like we've learned now. So elastic net is combination of L1 and L2 penalties to balance the strength of lead and lasso regression. It is useful when there are multiple correlated features or when both shrinkage and feature selection are desired. So you want both shrinkage and feature selection. Then you have cross validation. So you can use k-fold cross validation to determine the optimal value of the regularization parameter. I think that'll be particularly useful if you're working with regularization. So you want the best value of lambda that will give you the best result. I think we can put this. It's better to have this in dollar signs so we can have it the way it should be. Yeah. So use k-fold cross-validation to determine the optimal value of the regularization parameter lambda. This helps in selecting a model that generalizes well to unseen data, right? Then you can do feature scaling. So always standardize or normalize input features before applying regularized regression models. Regularization penalties are sensitive to the scale of features. So you want a normally distributed data set. That's why we did the scaling thing we did previously. So in summary, so to understand overfitting, model fits noise, and then you have poor generalization. All right. Use ridge or lasso regression. So if there's overfitting, then you can now think of, and overfitting is indicated, like we said, by model fitting the noise and leading to poor generalization. So how do you address that? You can use ridge or lasso regularization, these two add penalty term to shrink coefficients. Then ridge shrinks, that's L2 penalty, so it keeps all features but reduces coefficient magnitude. Then lasso shrinks and selects L1, so some coefficient becomes zero, that's automatic feature selection. Anything that goes to zero is not important. Then you can apply on data set, so standardized features split data, train and evaluate, then compare coefficients and performance so you can visualize and interpret results just like we did already. So this brings us to the end of this video. Let me know how helpful this is for you. And if there's something you would like me to do to try out, feel free to let me know. And of course, be sure to like and share so that more people can have access to this great content I have here. If you have not subscribed, please be sure to do that and hit the notification bell so you can always get alerted each time a new video is released. The membership is also available on my channel. Feel free to become a member to get special privileges like members only videos, or maybe you get to see some videos before other people see it and all that. All right. You can also have a one-on-one consultation with me, or get my PDF notes of my math classes on request if you become a member. All right. Till I come your way again, keep doing data right. Bye.